Hello everyone, Group 21 welcomes you to our presentation video on lifelong domain adaptation by consolidated internal distribution. This is a part of our CS771 course at IIT Kanpur. In this video, we'll explore the fascinating combination of unsupervised domain adaptation and continual learning. In unsupervised domain adaptation, this is a technique to adapt a model trained on a labeled source domain to an unlabeled target domain with differing data distributions. While in continual learning, we learn about the sequential tasks over time while returning the knowledge from previously learned tasks. So these are the two separate problems, and here in this video we want to join both of them. So here we'll address the challenges in combining unsupervised domain adaptation with continual learning, and we'll design an optimal algorithm for the same. We have some related works regarding this. In unsupervised domain adaptation, Wasserstein distance metric is used to handle vanishing gradients. In continual learning, model regularization is used to overcome catastrophic forgetting. Catastrophic forgetting is nothing but the problem by of forgetting the past events, past learned tasks. So we are going to club the problem of continual learning with unsupervised domain adaptation and design an algorithm that focuses on the gradual domain shifts in the environment. Now the problem statement is we are given a source domain S with the label training dataset. We also given a deep neural network F with learnable weights W that will correspond to some loss function L. Now the challenge in continual learning is drawn from drifted distributions, which arises due to the different data distributions in different domains. So this can lead to poor generalization during testing time. So we need a solution. So we have to update our trend model F somehow with unlabeled data of target domain that can avoid poor generalization without forgetting past experience. So what can we do? We can decompose our neural network F into a deep encoder phi and a classifier subnetwork H. So our key idea for the solution is to learn the distribution from source domain and align the target domain to this distribution. So by decomposing our neural network F, we get phi, which is the encoder that will encode the input space X into the embedded space Z that will be used to predict the labels, and we have subnetwork H, which is defined on the embedded space Z. Internal distribution is defined in the embedded space Z using Gaussian mixture model. In this solution, we define the internal distribution using Gaussian mixture model. So such that when the data domain changes, the internal distribution remains stable. It minimizes the distance between source and target domain. And to handle catastrophic forgetting, we'll select a small subset of the training data samples as representative data samples, also known as pseudo samples, and we'll store them in the memory buffer and we'll use them when required to align our target domain with the internal distribution, and thus we avoid catastrophic forgetting. The algorithm overview is as follows. First, we'll train the model on source domain and estimate the GMM corresponding to the source domain internal distribution. Initialize now we will initialize now we'll work with the internal distribution. Now we have no work to do with now the initial input distribution. We'll go with internal distribution. Now we'll initialize the memory buffer and generate pseudo dataset by taking samples from GMM. So in pseudo dataset, we'll select only those data samples whose confidence level is more than some preset threshold tau. Now we'll make use of memory buffer and we'll correspondingly update the GMM to align with data's domain and also update memory buffer with the current target domain. Now our objective function for the internal distribution looks like this. This contains two terms, two independent terms. First one is the loss function, which minimizes the loss function corresponding to the subnetwork H, and the second one is the domain alignment term, which aligns our target data domain with the internal distribution. So our theoretical justification is the internal distribution GMM remains stable across different target domains by aligning the distribution with source trend distributions. So our key terms are our error bound depends on the domain alignment, number of replayed samples, and the distance between learned and new tasks. Our solution works. Our solution ensures domain adaptation while preventing catastrophic forgetting by returning knowledge of past tasks via the GMM. Now we come to empirical validation, which is validation by experiments. So we use some UDA benchmarks and tested upon them by sequentially running the model on them, and it results quite good. Our LDA usage showed improved generalization on target domains, remains stable over time, and our solution also outperforms some traditional UDA methods. So our solution works quite good. Conclusions are we used Gaussian model mixture as an internal distribution by modifying our neural classifier, and in catastrophic forgetting we use experience replay by storing some pseudo samples in the memory buffer, and we have some future plans, like we can use internal distribution estimation other than GMM, address imbalanced data sets in UDA scenarios, investigate learning new classes incrementally. Thank you all.